I've decided that I would start recording a new set of lectures. These are comprehensive. They represent a large course, like a full course. I'm trying a variety of options in terms of a video, so it might be interesting. For example, I'll make myself disappear. So what I'm going to do in this particular lecture is I'm going to talk about the content of the course, make some general remarks, and then I'll go through a brief introduction to R and Julia and talk about connecting the two, and that is it. First of all, let's start with the course. Why do we have this course? It might be for several reasons, and so, for example, I might have sent you a link because you're working with me, and as part of our working together, I will be asking you to take this course and learn more about mathematical epidemiology. This course will be implemented as a topics course or as a reading course, and that's why it's called X8XYZ, because the number will change depending on how we implement the course. This is also a course for the students that I've met in a variety of contexts as teaching mathematical epidemiology in summer schools and the like. And if you want to go a bit further than what the time typically allows in those courses, then you would maybe be interested in this. Or more generally, you might be interested in learning more about mathematical epidemiology altogether, which would be nice. So in terms of who this course is for, I will stress that this is going to be on the mathematical side of things. So this is intended for students who are in mathematics, in physics or engineering. You need a strong background in mathematics to be able to make your way through the material. And for instance, I'm assuming that you know ODEs and related topics, and I will not go into detail, and I'm just going to assume that you understand what I'm talking about. If you don't, I still think this could be an interesting course for you, but it might require you to do quite a lot of work because, as I said, there is a certain amount of mathematics that you have to know in order to understand the course. Yes, let me make a, oops, this is not working really well. So if you want to get in touch with me, or well, if you're one of my students, you know how to do that. I'll just mention that every slide set begins with contains my email. I am very bad with emails, so if you email me and you don't get a reply, don't hesitate to try again. At some point it will reach my cortex and will be processed. And I really recommend tagging the material with something like MathEpi8XYZ, because otherwise it might go unread. One thing that I want to point out is that this course is available as a repo. All the slides that I'm going to present are available on the GitHub, whose address you have here. There's the slides, the code, and maybe some data samples. I will point out that the repo does not contain PDF of the references. I am, as much as possible, using open access references. This way anybody can access them, even if you don't have a university subscription to the material, but it still is going to be, I'm not going to, of course, infringe copyright by putting PDFs here. And one remark is I will also be talking about Wikipedia from time to time, and I want to point out that Wikipedia is a super tool, but it's a starting point for people learning stuff. So it's typically you can go to a Wikipedia page and start reading the material, but at the bottom there are references, and that's what I recommend looking at. The Wikipedia page is not a proper scientific reference. Another aspect of the course is that it will heavily depend on coding. So it's going to be a bit mixed. There are some of my lectures that include not so much coding or not any coding at all. It will be mostly mathematical, but some of the lectures will be intensely coding heavy. So if that's the case, what I would be using is R mostly, but also Julia a little bit. So there's a remark that I often make. I teach a math of data science class, and a lot of students are interested in learning Python. I'm not a very big fan of Python. It's also a very good language for this type of course, but I'm just more comfortable with R, and I will be using R and Julia a little bit for some aspects. There are instructions, and we're going to go through them in this lecture actually, on setting up R and Julia, but there's more instructions on the repo. You will find some code in the repo as well, and I'll just point out the reference for those who are really into proper epidemiology, not mathematical epidemiology, that this is a good book. I should point out that the references are clickable, so they don't appear. I might change the way the slides look to make the links a little bit more obvious, but a lot of references and everything that appears in the slides is clickable, and it will take you to the relevant place. So the slides that you're looking at right now, they're written in LaTeX, the math typesetting language that if you're taking this course, you probably know, and Beamer, and they're rendered using PDF LaTeX to make the PDF, and LaTeX and Knitr to go from the slides into LaTeX. So this is something I'll explain in more detail. It's a way of rendering the material. So what that means is that most of the figures that you will see in these lectures, they're actually generated as I compile things, and you will see also at the end of this lecture that every lecture that has R in it also has a corresponding R code where all the text is taken out and only the R remains. So videos, this is the first video. The videos will progressively become available on YouTube, and there's a playlist that you can click here that will take you to the YouTube video playlist. And also in the list of lectures, when I've recorded a video corresponding to a given lecture, there will be a link to the YouTube content right away. So what's the objectives of the course? The idea is to introduce you to mathematical epidemiology. I'm going to look at both the problems and the methods, the mathematical computational methods to look at this. And in particular, I'm going to be interested in modeling techniques, the mathematical and computational analysis of models, and I will stress that I think the computational analysis of models is also extremely important, and I will try as much as possible here to illustrate this. And I'm going to talk a little bit about the use of data. And I'm going to point out that it's important to do the four interactively, and I'll come back throughout the course on this topic. Now, I'm going to take two perspectives in the course. First of all, I am a mathematician, I'm a modeler, and so I think these are fun problems, interesting problems to look at. And if you're going to do work in mathematical epidemiology, you need to know the theory and understand what you're doing and so on. But mathematical epidemiology is also very important because it is a topic that is grounded in public health, of course, and these are very important topics to look at. You're trying to address the health of populations. And I think it's really important to understand your role as a modeler. So in a recent COVID crisis, for example, modelers were called on to provide guidance. It's important to know what you can do and what you cannot do with the models that you're using. And it's also important to know how to communicate with public health authorities. Okay, so I'm going to try to instill a little bit of this, even though this is a more mathematical analysis course. I am still going to try to make it clear sometimes where the connections are and how to address some specific problems. And that will come, for example, in the computational analysis side of things, where you're going to try to make the bridge with topics. And this is my last point here is an important one. It is important to know who you're talking to. So some of the problems we're going to look at here, they're mathematical in nature. So we're going to look at things like the local asymptotic stability or the global asymptotic stability of some equilibria. This is not what you communicate with, for example, public health authorities on. So you have to know, if you're talking to a bunch of mathematicians, it might be an interesting problem to bring up. If you're talking to someone who's interested in controlling a disease, the global asymptotic aspects, for example, are not really relevant. So if you are taking this course for credit because you're one of my graduate students, for example, then the mark for the course will be based on a project that you will have to write, and that project will be quite involved. Just a note in passing. So, as I said, the slides for the course are organized by lectures. Each lecture is meant to be about an hour and 15 minutes, and because I'm recording these videos and I'm not in a classroom subject to time, I might have a little bit of deviation, but the idea is that this corresponds to what at the University of Manitoba we teach on Tuesdays and Thursdays. These are an hour and 15 minute, 35 minutes long lectures. There should be 26 or 27 sets of slides because that's what a term is. And some content will go from one slide to a slide set to another. The title will make that explicit. And I aim, we'll see if I can do this, to produce the corresponding videos for all the slides. Now, second part, I want to make a few general remarks. So first of all, about modeling. I am, before I'm a mathematician, I'm also, most importantly, I would say that I'm interested in modeling. So I think modeling is really important. This is a crucial step in the mathematical epidemiology reasoning. It's a step that students often tend to neglect. They think they are going to have a model and that model is going to be usable out of the box right away, etc. I don't think that's the way you should proceed. So first of all, you should think outside the box. Don't let yourself be constrained by what you know how to do or what you know that you are going to be able to do. I think when the time comes, you might simplify a model or you might make some assumptions to make it more manageable from a mathematical point of view, but I think it's still very important to first let yourself not be hindered by considerations like, oh, but if I write it like this, I won't be able to do this step or this step. Okay? Take the time. Modeling is really, really important. A good model takes a lot of time. A good model should also be simple, but the important thing, the most important aspect is, I think, you should never hesitate to go back and modify your model at any step of the way. It's happened to me many times that I'm writing a paper, I think I have my model, I've done a lot of analysis and so on, and then I realize something doesn't click. And okay, we take the model, we start again. Okay, it's not a problem. Now, the mathematical analysis, I should say, so I started in the domain more than 20 years ago now, and at the time, mathematical analysis was the most important thing in papers. I'm a mathematician, I work in a department of mathematics. It's difficult for me to say, well, you should not be looking at the mathematical analysis, but I want to stress that you have to do it in a intelligent way. So I think it's really important to carry out the basic mathematical analysis of your models. What I aim to make as a point in this entire set of lectures is the fact that some basic properties of models, understanding them is going to allow you to, for example, if you are just interested in the computational work, still some of the things we're going to extract from the mathematical analysis is going to be very, very important. Okay, it's going to help a lot. And so this is my last point here. Do as much as possible. But, for example, one thing, don't hesitate to put things in an appendix. In a modern mathematical epidemiology paper, you should be focusing on the problem itself. How you analyze the problem from a mathematical point of view is perhaps detrimental to the flow of your presentation. So it really depends. It could be you've come up with a very interesting way to analyze the model, and in this case, this should be front and center. But if your problem is a real epidemiology problem that you're trying to approach using mathematical epidemiology, then perhaps the proofs can be moved to an appendix. Okay. Now, the numerics, for me, are very, very important, but they have to be used in a very clever and rigorous way. So the numerics complement the mathematical analysis. They don't illustrate mathematical analysis. One thing that gets me completely nuts is that second point here. You will see a lot of papers where the authors have proved the global asymptotic stability of an equilibrium point, for example. And they are going to show you simulations of the model with trajectories tending to that equilibrium. But it's useless. I mean, in my view, if that is all that you're doing the numerics for, it's just as well not to do it. Because if your mathematical analysis is correct, then yes, you know solutions are going to go there. Now, there's a lot of interesting questions that come from even having something like this. So how fast, for example, do you go to that equilibrium? Or how does that equilibrium vary as a function of parameters and so on? But usually that's what you want to approach, okay? Don't just show trajectories going to an equilibrium. Even if you change the parameters a little bit and you show that I'll try to make this clear throughout the course. Okay, I'll give a lot of examples of how you would plot things and so on. Now, what I think the strength of our domain is that it allows us to test scenarios. This is something that in real life is difficult to do. Okay, because you can't just say, okay, suppose I were to vaccinate only half of the people that I am vaccinating at present, what would happen? In real life, this is not possible. But in a model, we can see the effect. So don't take the results of the model sort of literally, but the effects are there. And this is, I think, the most important contribution of modeling in epidemiology. It's this studying of scenarios. Okay. And the last point I want to make, which is often neglected, is that a good figure may take you a lot of time to produce, but it's really worth it. If you have an interesting result, it can take several days to come up with the proper figure. If it takes you a minute to make a figure, it's probably not a figure that's worth presenting, okay? Because you really have to think about how to present stuff. Now, another aspect of mathematical epidemiology that I will be talking about from time to time is the use of data. Now, I will point out that, for example, during COVID-19, what became clear is that data has become much more available than it was. So, for example, I've lived through a variety of pandemic events or disease spread events. So, for example, the 2009 influenza pandemic and stuff like this. And the amount of data that became available during the COVID pandemic is really great. But I'm going to put a sort of tamper on this. This is not a course about statistics, which is really the domain that uses data the most. This is a modeling course. And so I think it's really important that you are extremely aware of the context. So look at the data, know what the numbers are. If you're doing a model and, for example, the problem you're looking at is about, I don't know, 10 cases happening in a jurisdiction over a period of a week, your model, if it produces 1 million cases, then it's wrong, okay? So it's really important to be aware of the context, to be acutely aware of the context, but it's also important to not think that everything has to be data-driven. And I'll cite a very good friend of mine, unfortunately deceased now, who used to point out that if your model and the data disagree, typically, it is a good thing to question the quality of your data. And that segs me into this. So Fred was someone who, I mean, in this type of, I'm teaching about mathematical epidemiology, and I taught mathematical epidemiology with Fred in a variety of contexts. And it's just to acknowledge that this is the type of course that Fred would, I hope Fred would have taught. And in particular, there is that citation that he loved by Maslow. When you learn how to use a hammer, everything looks like a nail. So his teaching of mathematical epidemiology always stressed the fact that you should not learn how to use a single hammer. You have to have multiple hammers because you have to avoid getting trapped into one single modeling idea. Okay. So before I press on, these are some notations that I'll be using throughout the course, throughout the slides. So just an EP is an equilibrium point, a DFE is what we call a disease-free equilibrium, an EEP is an endemic equilibrium point, LAS means locally asymptotically stable or local asymptotic stability, and GAS means globally asymptotically stable or global asymptotic stability. We'll come back to that, but I'm just putting those out here. And the last thing that I really want to stress, and I think this is really important, the way I'm presenting this course, the way I've structured it, is based on my personal history, my itinerary through MathEpi. So some of the things that I'm going to say, I have understood them one way, and I'm going to explain them to you based on what I have understood, but other people might have understood them slightly differently. I'm going to focus on topics that I like, and I'm going to skip some topics that I like less. That doesn't mean those topics are not good and worthy of consideration. It simply means that probably I don't understand them well enough to talk to you about it. And so don't trust me blindly. And I would say shop around. There's a lot of people doing mathematical epidemiology and doing instruction in mathematical epidemiology. And I think it's important to be aware of a variety of ways of thinking. Okay, and now I'm going to skip to the second part of this lecture, which is I'm going to be talking about R mostly, a little bit about Julia and the connection between R and Julia later, but mostly R being my main topic here is going to, my main tool for numerics is going to be what I'll focus on. So, as I said, most of the course, the code is in R. I will show you that in a second. The code that you see in these slides is executable, and it's executed to create the slides that you're seeing. I'm generating the equivalent, so whatever code you see, for example, in this lecture, is going to be generated as an R file. So this here, the slides are created, the format is RNW, and it's LaTeX and R mixed. But I'm also generating, when, of course, I have R in the slides, I'm generating a corresponding R file that has all the LaTeX stripped out and just contains the code. So you can play with that one directly. And these are stored in the code directory, in the repository. Now, why am I using R and what is R? R is an open source version of a program that was called S. It appeared quite some time ago. We're at, this is not up to date, this should be 4.5. So we're at version 4.5. And one of the things I really like in this, so R was originally for stats, but it's evolved quite a lot. And one of the things I like, whether it's for stats or for math, is that the code base of R uses a lot of C and Fortran. So essentially, for example, we'll be using DESolve, which is a package to solve differential equations numerically. DESolve, if you read it, it's an interface to the Fortran functions, LSODA, LSODAR, etc., of the ODE pack correction, which is a really well-established numerical package for solving differential equations. It's got other Fortran routines and C. So that means it's programmed in very low-level languages, and it's really fast. Okay. Another advantage that I like of R, it's true of Python, it's true of a lot of languages, but Python and R are essentially the most two active languages for this. It's a very active community on the web, and therefore that means that it's very easy to find answers to problems. Now, as a development environment, there's a terminal version of R. It's not super friendly. There's a slightly nicer terminal which is called Radeon. I'll point out that it's important, I think, from time to time to use this capacity tool, which is to use RScript, the name of your file, and it's useful, for example, to run as an automated task, but it's also useful in another context, which I'll come back to in a second, which is to run without the information that you have already in memory being in memory. Okay, I'll explain that in a second when I show you RStudio. So that's the sort of low-level way of doing it, but also there are two main development environments, and the most famous one is now RStudio, which has become a reference. POSIT, which is the company that makes RStudio, well, I mean, that's how it's called now. POSIT has done a lot of work also developing R, so they are really useful. R also integrates really well into Jupyter Notebooks. I'm not going to discuss this too much, but this is also an option that you have. So what I want to do now is just spend a couple of minutes showing you our studio and making a couple of remarks about our studio. Okay, so I'm back. I've initiated an RStudio instance, and so here you can see actually this is this lecture here. So this is, if you're used to doing Beamer presentation, this is a Beamer presentation. It's standard LaTeX, except that there are in here some places where, for example, I have, this is R code. And so what's going to happen is that this chunk, it's called a code chunk, this code chunk will be evaluated when I hit compile PDF here. And the result of this is that first the R chunks will be evaluated, then if there's any figures that need to be made, they are made, and then this generates a LaTeX file, which doesn't have any R embedded anymore. And when this LaTeX file is compiled, you get the slides that I have here. And I'm not going to do that right now. The one thing I wanted to mention, so this is the RStudio development interface. So here you have the code. Here you have a console, which is just your R running. So you see there 4.5.1, which is the latest version. There's a terminal as well if you need to use the command line to interact with the system. So here this is, here I'm recording. I normally work under Linux, but these videos I record under Windows. And so here you see I'm running in MingWin, which is a Unix emulator under Windows. There's also background jobs. Then here you have a window that will contain either the files, the plots if you make any while you're working on code. It can list what packages are installed. There's the help browser will be here, for example. The viewer, let's not worry about this in presentation, let's not worry. I mean, the ones you will be using the most are files, which allow you to browse the files, plots, and help. And then finally here on the top right you have, not finally, so on the top right you have the environment, which for now is empty, but let me, for example, evaluate this. Would simply say, okay, I've made a vector, I'll come back to that in a second, but I've made a vector with 10 entries, and you see I'm going to have all the variables, the tables, the functions, everything is going to appear in the global environment here. The history is the list of commands you used. Connections, let not worry. You have also a GitHub interface, so here you can see that, for example, it's got a bunch of things that I should commit. It thinks. One thing I should mention also is that in RStudio, what is really useful is to make what's called a project. So here, this is a project. This is the list of projects that I've looked at recently. And the idea with a project is that, so here I have one for these slides, which you have on the course repo. Okay, and the good thing is that, for example, if you're in a project, RStudio communicates with R and says, okay, this is the directory we're working in by default, which is the top level directory of your project, and a variety of things like this are made much easier with using this. The one thing I want to stress, and I always stress this with when I'm teaching and I'm using R, I really recommend, it's not an obligation, but I really recommend, I'm not seeing if this is appearing. Let me see if that shows. No, it doesn't show. Okay, there's in the tools here, there's an option, for some reason it's not showing. There's an option for global options. Yes, so if you go to tools in the bar at the top, and then you go to global options, I really recommend that here on this first page, you say don't save, so never save the workspace to our data. And also, okay, this is okay, but do not restore our data. Okay, this is an important characteristic, because if you don't do that, then what happens is R saves its status. But what's really important mostly here is actually to I'll try to make this come back to a decent size. What's important when you're starting is for the memory to be clean, because what you do should be saved in your scripts, which are these files, okay, whether it's the RMW file or a common regular R file. And the script is what you distribute to your collaborators, for example. If you have things saved from the environment that are not generated by your script, then your collaborators are not going to be able to load that information. So you have to ensure that things start fresh, so that you get an error if you haven't defined something. Okay, because after a while you see that that right-hand side will become extremely populated. And the problem is, if you save that R data file, then this is what becomes the norm. Okay? So that's why I really recommend not saving the data and not restoring it on startup. Okay, so we're back to the regular slides. I just wanted to point this out about the state of RStudio when it starts up. So a few additional things that we might see from time to time. RStudio server is something like, as a Unix user, is very useful. I have it running on most of my machines, therefore I can connect through the web via a web interface and run R on the machine remotely using a web interface. This only runs under Linux. Shiny is something I might talk about. It's a really good way of creating interactive visions of R. And it's a really good way, for instance, to collaborate with public health people, because you essentially give them an interface where they can play with the parameters of your model and see what the model says when they change the parameters themselves. Shiny server is like RStudio server. It runs Shiny apps on a Linux server. You'll see examples of that throughout the course. R Markdown is typically what is used the most now. It's Markdown, which is a very simple text editing software, and it's really a very easy way to create nice looking reports or web pages. And RSweave or Knitr is what I'm using right now to create those slides. Now, R is an interactive language. So when you have an R console, like I showed you in the RStudio interface, here you can type commands. They are evaluated off right away. And that allows you to run in real time. But remember what I was saying about ensuring that you put everything that you want to make sure that you remember in a script, because the sort of bad counterpart to something being interactive is that sometimes you'll end up doing manipulations that interactively, and you don't forget that you've done them, and then the next time around on another computer, or you send to a collaborator, and they have no idea what you're talking about because the manipulations you did were interactive, you didn't save them in the script. Okay. R is quite similar to MATLAB, but it's quite different. I have this slide for because I used to encounter a lot of engineering students who would be more familiar with MATLAB. I don't think now this is really the problem. So, very brief introduction to R now. First of all, assignment. There's two ways to assign values to a variable. It's either the classic x equals 10, but there's also this sort of algorithmic inspired way of writing things, which I think is quite cool. I don't really care, but I'll just point out that if you're talking to someone who's been using R for a while, probably coming from another context, I'm not sure, but you can run into big arguments if you're not using this type of explanation. In R, one of the very important structures is what are called lists. So there's no, a list is a basic all-purpose thing. You can create an empty list by just going empty list. You can store anything in a list. So for example, here I'm making an empty list and I'm storing an entry that's called A, and I give it the value 10, B is 3, and then this is another way to create an entry. I'm saying that this is an entry called another name, and then it's proof, whatever. And so I could also do that right away by just assigning, instead of assigning an empty list and putting entries in there, I could just say L is the list with A equals 10, B equals 3, and another name. List entries are accessed either by their, so this is the first entry in the list, where you see that the first entry in the list has the name A and value 10. If I put a double square brackets, then I access directly the content of the second entry here. I can also put a $sign, $A is 10, or I can put a string and I get the same result. This is very useful, in particular this string format, because you can, for example, say I have several years of data and then I have a list entry for each year. Then I can do a for loop on these years and access the entries that way by using just a string. Vectors work very similarly to many others. If I do 1 to 10, it's the list of entry of integers from 1 to 10. C is either used to make a vector, so I could have C 1, 2, 3, etc., or to append entries to a vector. So here, for example, I'm appending 12 to X, and so my vector is now 1 to 10 and 12. Vectors, one remark is here, for example, I'm making a vector of red and blue. These are strings. And so if I add an entry to this vector, it ends up being a string, because vectors and matrices have one type of entry. So whatever you use to define them is what they are for the rest of times. And this is important to bear in mind because it's a source of problems where you think you're assigning some type of value, but instead you're assigning, for example, here a string instead of an integer. That would not be the problem with lists. So matrices that we are going to use a lot in this course, they're defined. I can make a matrix of zeros. In this case, I have to say how many rows and columns it has. Or I can make a matrix with some type of entries, 1, 2, 3, 4. Here, for example, this is a vector with 1, 2, 3, 4. And I say it's got 2 rows and 2 columns. Like many other languages, the order is column first. So 1, 2, 3, 4 gives you 1, 2, 3, 4, like this. If you want to enter entries by row, then you say by row equals true. Okay. You can oops. Yes, sorry. One quirk of R that I have yet to understand is that if you write A, B, like so, normally this is matrix product, but in R it's not, it's the Hadamard product, which is typically prefixed by dot in most other languages. If you want to use a proper matrix product, you have to surround that star by percent signs. Okay, so a standard matrix multiplication is A percent star percent B. And I point that out because, okay, so if you have a matrix that is non-conformable, so for example, if you're expecting that you have to have products in a certain way, then the star would typically throw errors. But the problem is, in modeling, most of the time our matrices are square. And if they are square, then whether you're taking the Hadamard product or the matrix product is not clear right away, and that's a source of errors. Vector operations, there's also one interesting quirk that is annoying. If I have a vector from 1 to 10, so the advantage of R is that it's not really typed. And the disadvantage of R is that it's not really typed. So if I say x plus 1, this should yield an error. Okay, this is a vector to which I'm adding a scalar. No, it doesn't. What it does is it creates a vector of ones of the same size as x and just adds the two together. So you can see that x plus 1 is actually just that vector here. One annoying thing is that there's no end keyword, like there is actually in Julia. I'll talk about Julia briefly at the end of the lecture. But in R, there's no end keyword, so you have to use length. That's for list of vectors, number of characters for chains, dimension for matrices, and remember it returns one, the number of rows and the number of columns. You can also use n row, n col, but anyway, you'll always be using some function to know what the last entry in your matrix or vector is. Data frames are used to be a feature of R. I think now they've permeated a lot of other languages. They're matrices with additional characteristics. They can contain all sorts of entries, so they're not like matrices, they're more like lists, and actually they're very similar. So I could create a data frame here, for example. What I'm doing is I'm taking a data frame, I'm naming the first column, column 1. R unif is take a uniform number randomly, and if I don't specify, it's between 0 and 1. So this is a function. It gives me 9 random numbers between the values 0 and 1. So this is the content of column 1. And you can see that color, what I'm doing is I'm taking a random number between 0 and 9 random numbers between 0 and 9 and 1. And if they're less than 1, than half, sorry, if else is, if the condition is true, then the first entry is realized, and if a condition is false, it's like this. So what I'm doing is if it's less than a half, if a number that I've picked, not that one, okay, a different number, it's less than a half, I put red, and if it's more than a half, I put green. And so here you have a data frame that has these. Data frames, you can access some characteristics, for example, using the function summary. So summary, for example, for column A, which is a numerical column, it will give me the minimum, first quarter, second quartile, sorry, median, mean, third quartile, and max. For categorical variable is just going to say how many entries there are, what type of characters there are, and so on. And I'll point out that that function summary also works with a variety of other fields, other data types. And actually a lot of people who develop R packages also implement a version of summary if they have a data type or data types in their package, they implement a summary function. So it can be very useful to name position, rows, columns, etc. So here, for example, I'm making a vector in which I say, and this is a good way, and you'll see when we use simulations, this is a good way to name your parameters in a model. So this is a vector that has entries that are named alpha, beta, gamma, delta, and I can access these entries by just saying v of and the string this. Sometimes, if you do that, I'll point out that your result will come out that way. So it can be useful, because that can be a source of problem, to actually ensure that the result is a numeric result. And as dot something is a function that's defined for a variety of data types. As numeric just converts it to numeric. For example, you could take a matrix. This is something we'll do often. You have a matrix, you want to make it into a data frame. You would say as dot data frame of the matrix, and you get the data frame, or vice versa, as dot matrix of a data frame will give you the corresponding matrix. Although, because it's a matrix, by the remark I was making earlier, it would contain only entries of the same type. So, for example, if you have strings and integers in your matrix, in your data frame, the conversion will yield interesting results. You can also assign a name afterwards. So here I'm making a vector with 1, 2, 3, and then I'm saying that the names of the vector are like this. There's going to be different names for things. So for example, if I have a matrix, here I'm doing the same. I'm taking my matrix with 1, 2, 3, 4. And if I want to name things, then here I have to say row name and call names. Okay, and then this is what the matrix looks like. I can still access it by position. So the 1, 2 entry in that matrix is 2, but I can also access it by name. So alpha doodle is 2 as well. There's a new data type that I'm not going to comment here, but that we'll see throughout the lectures, which is called tibbles, which are tables. They're part of an environment called the tidyverse. It's a set of libraries that are mostly dealing with data wrangling, but they do a lot of things. We'll use them for plotting. ggplot2, which is an R function, is part of a tidyverse, or affiliated with a tidyverse. There's some variation with a data frame, you'll see, and the important thing is to know what a tibble is, because if you use any tidyverse type package or function, then the output will be a tibble, not a data frame. For flow control, it's quite easy. You test if a condition is true by putting it between parentheses. So you have and we'll see a lot of that. So I'm not going into details because there'll be a lot more details. You can omit the curly braces, but even if I would recommend always having the curly braces to really make it clear what the blocks are. You have if, else, if, etc. The loops, the loops are quite flexible. You can either, for example, say, essentially it iterates over a set. So the set can be, for example, integers from 1 to 10. They can be integers in a vector that I have, but I could also say, well, I have some names and I want to iterate over the names. And here n is going to be a string. Or I have a bunch of things and I can actually just, for example, say, oh, okay, is it a string or something else? And I can detail things. So loops are very flexible. One thing that is even better, I would say, is lapply, so list apply. There's a few other functions in the same frame of mind. There's sapply, vapply, mapply. We'll see some of them as we go. So the idea of these functions is to, and there's even apply without anything else. But lapply is the one we'll use the most in this course. The idea is that it applies a function to each entry in the list. And the reason why I think it's really good to know this as a programmer doing modeling is that there is parallel versions of these functions. Now I'm going to use mostly Future, which is a newer library, but there's also a PAR-lapply, which uses parallel library. Future, I think, is better. But altogether, and I will see some examples throughout the lectures, I think it's worth really understanding how lapply works and how to use it, because it is going to allow you to do things in parallel, for example, in a very easy way. So let me show you an example. I have a list. I'm going to put in each entry in the list the result of a uniform number generator with the number of entries, the current position in the list. So the first entry has one random number between 0 and 1, the second has 2, the third has 3. Okay? And now I'm going to apply, for example, the function mean to each entry in the list. So the first is, of course, the same as the entry, but for the second, we've applied mean to these two entries, and that's the result. And the third is the mean over the 3 entries that we chose at random. And you'll see that notice this indicates that the result is a list. Okay. If I want to make a vector, I can, for example, use the function unlist, but delists a list, so this gives me a vector, or I could use also sapply, which has results as a vector. Okay. One thing that's interesting is that you can use a function in the function call. So, for example, let me make a list that is a little less trivial than the one I was making before. I'm going to take a list. Each entry in the list is going to contain a list itself. And that list is going to have, the first entry is going to be called A, and it's going to have I randomly generated numbers, and the second entry is going to be called B, and it's going to have 2 times the number of, 2 times the value of I, random numbers between 0 and 1. And here I could get a vector, for example, where I'm applying the function that I've defined here, which is simply a function to each entry x being a list entry. Okay, I'm going to apply the function length of b. So my list L consists in 10 sublists. Each of these sublists has 2 entries, 2 fields. One is A, one is B. And here I'm saying, just give me, I'm applying to L that function. So for each of these list entries, give me the length of B. And you can see this is exactly what you could plan. I mean, it's 2, 4, 10, 6, 8, etc. Okay. Another thing that we use a lot is what's called expand grid. So for example, suppose I want to vary 3 parameters. So these have to be, like I'm giving a range for each parameter. I'm giving a list or a vector of the parameter values. They don't have to be, they can be numbers, they can be strings, etc. As usual, a given vector will have only one type of entry, but I'm giving a certain number of vectors. So here I'm varying from 1 to 10 in 10 values. Okay, I'm not giving the increment, I'm just saying I want 10 values between 1 and 10, progressively. I want 10 values from 0 to 1, so I want the interval 0 to 1 cut in 10, and I want 10 values between -1 and 1. Then I can do expand grid of this list, and what I'm going to get is temp here is going to have 1 here, because that's going to be the first entry, 0, -1. Then it's going to have 1, 0, and the second entry in this vector, 1, 0, and the third entry, and so on. It does all the combinations of these three parameters. And then you can just create a list with that. And for example, when we're doing parallel computing, this is what we are going to feed into the loop, a variety of cases like this. And you'll see that later. One other advantage of R, so I have a paper that you can take a look at. I mean, there's many others, but this was something I wrote actually just before COVID. It came out, I think, the first week of January 2020. But I give there a few techniques for acquiring data. And one thing that I want to point out is that I've said that already. It's very easy now to get data, and I think it's important to know what data is available and to try to use it. As I said, not necessarily because you want to fit the results, but just to be aware of the things. So let me not get into that too much. I mean, there's a lot of detail that you can think about the data. There's closed data, which is typically generated, for example, by companies or even research institutions. Typically, it comes with restrictions, but as of recently, there's been quite a lot of open data. I'll just point out that even if it's open, you may have to check what the rules are for using that data. Okay, so it's not because it's available on the web that you can use it for anything. I'll just point out I've put a few here where it's something that is quite recent, and here there's a lot of links that you can look at that are going to, they're clickable, all of them. These are open data sets that you can, where you can find a lot of information. So for example, the WHO, the World Health Organization, as a modeler for infectious diseases, has a lot of data that you can access through their open data portals, etc. So let me show you an example of using, for instance, data just to get a context. So here I'm using and to show you how easy it is, I'm using three libraries. One is ggplot2, which is for plotting. Scales is also for plotting, and WBStats is World Bank Stats, so it's a library that accesses World Bank data directly. And just to show you how incredibly easy it is to get the data, here my call is just to get, I want to get the population of Canada, so I'm selecting the country Canada. The indicator is the total population, okay? So you have to search. I know that this is one search index. MRV means most recent values, so I'm just taking a very long thing. Typically, we don't have that much data, but by taking a larger number, it doesn't matter. It just gets the first data point available. And this is just internal. I don't want the wide return, I want the old style return, but never mind. And then here, this is just the plot. ggplot is, okay, it's a little annoying, and I'll show a variety of ways of plotting, but it produces really nice looking graphs. Okay, so here I'm plotting that data that I got. I'm using as x-axis the date, as y-axis the value that I got from the data. I'm saying it's a line, these are the title and etc. And then I'm putting a label. This is just to ensure that the right-hand side of the plot has millions instead of just scientific notation. So what I'm doing is I'm scaling the numbers on the right, dividing them by millions, And this way I get numbers. And theme minimal just means, okay, use a theme. So ggplot has themes, and I'm using a theme which is quite light. And this is what I get. So this runs in a second. And essentially in 1 second, you can get the data for the population of Canada from 1960 to, it's typically a year or two late, but okay. So this is what I want to point out. Now let's switch to a very important component of models here in mathematical epidemiology, which is going to be solving differential equations. And so in R, we use the dsolve library. There are a few others, but that's a very good starting point. As I already pointed out, this library has been around for quite a while. ODE-PAC, as I said, the content of a library. ODE-PAC is Fortran 77. It's been updated, but it was developed in the late 70s. So it's been optimized since. Okay. So let me show you one of the simplest possible ODEs. I'm going to solve the logistic equation. Create a solution to the logistic equation. So here, this is a little trick I'll just point it out. So you're essentially, as with all other languages, you need to define the right-hand side function, which is going to be evaluated at any point t in time. So here, this is an autonomous equation, so it's not going to be used. X is the state, and p is the vector of parameters. And here what I'm doing is I'm going to name, let's look at this one. I'm making the initial condition. I'm saying I'm starting with n equals 50. So remember, you can name the entries in a vector. If you do so, then X is passed to the solver with this name. Okay, the initial condition and then later on. So that means that I can just use n, but I have to unlist it. Otherwise it's x $n or x of n. Depends, I don't remember if it's no, it's a vector, so it's x of n. But if I say with as list of x, what it does is it transforms x into a list, and then assumes that this list is known. So, okay, this is a little trick. Actually, this should be indented. This is a little trick that allows you to use the name n. I could do the same. I could say with as list of c, and I think I do so in the next, yes, I do so in the next slide, so I won't go into details here. So this is one way of doing it. Set the parameters. I have the parameters, they need to be a list, okay? The initial conditions are a vector, the parameters are a list. That's not great. And the times are the times at which the solution, not at which they are evaluated, because it's an internal mechanism to whatever solver you're using, but the times at which the solution is reported to you. So that's very useful, for example, if you're trying to fit data, because you can do the times at which you have the data points. So here I'm just saying report the solution at times 0 to 100 by steps of 1. Okay, so from 0, 1, 2, etc. And then the call is just, I'm assigning the solution to this. I'm calling ODE, which takes the default function in dsolve. With initial condition provided, the times at which I want the solution, the name of the function that is used to create the solution, and the parameters, if any. I mean, you don't have to have parameters, but here I have them, so I'm using them. Now, as I was hinting, I could also make my life a little simpler and even say, I'm also within this. So here I'm saying the state and the parameters are put as a list, and I'm using these without their list structure. Okay, essentially I'm returning them, so that means I can use them without, if you remember the previous one, I was accessing parameter places. Here I was saying in the list R get, in the list params which has the name p locally, get the parameter r. Here I can just use r because I've put the parameters p here. Okay, same thing, etc. The default method is lsoda, which is nice because it automatically switches between stiff and non-stiff problems, methods for stiff and non-stiff problems. You can change stuff, you can do a lot of things. I won't get into details. We might see some more specific examples later. Now let me very quickly, in about 10 minutes, talk to you about Julia a little bit. This is something I'm less familiar with, but I've started using in certain circumstances, which I will highlight. So it's a high-level, high-performance dynamic programming language. It's really designed for scientific computing, very much the same way as R and so on. And I'll point out what their aim is to solve what they call the two-language problem, which is essentially that if you want, when you're coding, prototyping is typically very easy with languages like R. It's easy to write, it's flexible, but the problem is that typically it's slower. And so, for example, if you use Python in particular, it's a very slow language for some stuff. And in scientific applications, we're often looking at trying to do large-scale computations, and in that case, languages like R, etc., are not really good. Now, on the production side, when you're using stuff, well, if you're doing large-scale problems, you want C, C++, Fortran, which are really, really fast. But the problem is that it's harder to learn, and it's also more unforgiving. So there's a lot of time. For example, I started in C years and years ago, and the debugging stage is really annoying. Okay, so the idea of Julia is to try to have something that is as fast as the C, C++, Fortran type stuff, but with something, with a language that is a bit easier to use than those languages. I'm not going to get too much into the details. I'll just point out that it's got just-in-time compiling. So that means that when you're running code, typically before it runs it, it pre-compiles it, which means that you get code which is really quick. It's parallel automatically. Essentially, it's I'll show you some examples. The package manager is quite good, so there's a variety of things that are easy. So compared to R, one of the main features is that this is a typed language. So it's much more unforgiving. I was giving the example earlier of a vector in R to which you add a 1, and R automatically makes a vector of 1s, which it adds to every entry. This is not something that Julia will allow you to do, fortunately. So there's a variety of types. I'll go quickly over this because I don't think it's really worth spending some time. This is for you to look at if you're interested in learning more about this. You can define matrices, vectors, very similarly to the way you're doing them in R, except that this is a more perhaps straightforward way of doing things. For loops, while loops, if else. This, in passing, the syntax of Julia is very similar to the syntax of Python. It's more similar to Python than it is to R, and in particular, it requires you can't just have a curly brace opening and closing a block without indentation, which I think you should always indent even if you have opening and curly braces. But in Julia, very much like in Python, every block, you see if this is a block because it's right indented. You define functions this way. Okay, I'm not going to go into details. There's a capacity that's called multiple dispatch, which is quite interesting. The idea being that you can make a method that you would say, for example, if I combine two numbers, it's going to be the sum of the two numbers. If I have two strings, I'm going to take the strings and put an empty space between them. And if I combine a number of a number and a string, if x is a number and y is a string, I'm just going to repeat the string. And so, for example, this same function applies to a variety of arguments if you've defined a function properly. There's a lot of packages. Data frames is one that we'll use from time to time if we're using Julia, because it allows to put things in a context that R understands, or to get data from R and understand it. The other one that we'll use a lot, of course, is differential equations. I'll have a few examples throughout the course. That's just a plot. Just a remark in passing, here I'm generating a vector, and if I want to apply the function to each entry in the vector, I have to dot it. Okay, it just says take the function f, so it's not, I mean, you have to explicitly say you're vectorizing the function. There's a bunch of macros, so here, for example, if I say time, then I get the time that it takes, and etc. to evaluate this. I'll point out there is a file with the same name as these slides in the code directory, but that ends with .jl. It has all this code that I'm showing you here in a file that you can run through Julia, the same way as we have a thing for the R code. Let me just show you the one that might be the most important to you, using the differential equations suite. Okay. Actually, an interesting thing is for now, because one thing we see in this course is continuous time Markov chains. For now, continuous time Markov chains are also part of differential equations. I saw somewhere that they might be branching out, I mean, making a specific package, but for the moment, if you want to do continuous time Markov chains, you also use differential equations, which is a little bizarre to me, but never mind. Okay, so I take a differential, so this is how you say that you want to use these packages, differential equations and plot. I'm doing exactly the same thing, essentially, as we did with the R code. I have U, which is the state here, I mean, P, which is the parameters, and T, which is the time. So the order is not the same, the arguments, but the idea is the same. Okay, U, state, P, parameters, and T, time. In R, it's T, state, well, time, state, and parameters. Here it's state, parameters, and time. This simply says that we are taking the content of P and assigning it to R and K. Okay, and you can do the two at once by just saying R and K are P.R and P.K, and I just return a logistic there. Set up the problem, take the initial value. It's the same problem as I had before, the time span. So here you don't indicate at what, I mean, you can also do so, but in a different way. Here I'm indicating the interval on which I want the solution. Set the parameters, and then set up a problem. So this is an ODE problem that uses that function logistic growth, the initial condition U0, the time span, and the parameters P. Solve and plot. I'm not going to show you the plot. This is the logistic equation. I was saying earlier, don't show plots, but you know what's happening. The carrying capacity is 100. The solution increases from 50 to 100 and converges to 100. One thing that is really cool, and that is not present in R, so callbacks or event handling is present in R. But this particular one, is really, really useful sometimes. So the callbacks or events in R, it's essentially a way for your numerical solver to react to certain events. The events can be my solution is going above a certain thing, or the time is bigger than so on and so forth. But one that is really important here is this one. So there's a callback in Julia. It's called a callback, not an event, but essentially the same. So there's a callback called positive domain, which is super useful for modeling. So you're simply saying, okay, I'm going to say positive domain is the callback positive domain, and I set the callbacks. So I could have a list of callbacks. For example, one of the callbacks could be I have an impulsive differential equation, and from time to time I put an impulse. But here, the only one I'm considering is the fact that I want a positive domain. And so now I can change my problem from before. Of course, with a logistic equation, it's not going to be a problem, but it is a problem elsewhere. I can change my problem. Remember here I had solve of just, problem is this. Here I'm saying, okay, the problem is still the same, but I'm adding the callbacks that I've just defined. This is the name of the integrator. Okay, it doesn't matter. Changing the solution, the tolerances, this is options that you might have to change, and this is I'm saving every half time unit the solution. And so what that callback does is if you have a solution that is becoming negative because of the integration step, for example, being a bit too big or whatever reason, it decreases the integration step. So it doesn't do. Oftentimes, you'll end up dealing with solutions becoming negative by, for example, saying, well, if I detect that the solution is negative, I'll make it equal to 0. Here, that's not what it does. It reduces the time step so that the solution doesn't shoot through 0. So if you know that your system has non-negative solutions, this is a good thing to put in there if you start noticing that your solutions become negative. So this is, for me, the main reason for using Julia over R. When I start to have problems that become negative, that's what I do. So if you want to get started in R, in Julia, these are links that you can look at. I'll just point out the forum is really reactive and useful. So I've had good experiences asking questions because I couldn't understand anything. Julia has, they say they have a nicer learning curve than C or C++ or Fortran, but I'm not entirely convinced. So you might be there often. And the last thing I wanted to point out is that you can actually get R and Julia to work together. That reminds me. In all my slides, you see those stupid graphics. I should point out these are made with AI. It's the only thing that's made in AI with AI in these slides. I have yet for some of the code. Sometimes I get it to check for the code, etc. But the transition slides, the graphics, they're all made with typically Gemini, I think. So it's just a word of a disclaimer. Pictures be AI. Okay, so it can be interesting to call one language from the other. And I might show you some examples throughout the lectures. But very briefly, essentially, for example, the example that I was just giving, I can be interested in doing some work in R, but then using Julia to do the integration because I want to handle this non-negativity well. I will point out one way is harder than the other. Calling Julia from R is, in my experience, hard. Not always trivial. And I use Linux, which is typically the best environment for doing this type of thing. But still, it is prone to problems. So it is feasible. I've got it to work in several machines, but for example, it is not something that I can steadily reproduce. So I have some machines where I'm managing to do the calls and others where I'm not. It works really well the other way. So calling R from Julia works really well. So there's a package called rcall, which allows you to call R. And so here I'm giving you a very simple example. This piece of code that you're seeing here is R. The overall code is in Julia. Okay, so once you've loaded stuff, essentially I'm creating a data frame in R, and then I'm getting the results. So what happens is an R session runs in the background, is run in the background, and in there I'm defining my R data frame. Okay. And then from Julia, once it's run, it's in the background, but it's not terminated. I can query it, and so what I'm doing here is I'm getting rget this data frame, and then I could, for example, plot it. I'm not going to show you the plot, but this is something that will work. And the last, very last slide of this lecture, which I hope is not too long compared to what I was planning. I think it's a little over an hour, 15 minutes. But close to an hour and a half. Most of the lectures will be right on time. This one is a bit long. This is just to point out, I have code that I'm not showing you, but that you will see in the slides, the RNW. The last bit of the slides creates code in the code subfolder. For some reason, this is not going to the next line. But anyway, it's creating code that is the RNW, but without any LaTeX. Okay, and you can run this code to get all the R that I've showed here. I mean, for the moment, there's not a lot, but in the other lectures, when we have R, it will be useful.